we proceed to the next presentation, another very interesting presentation and conversation as proposed. It's Mr. Alexander Impma and Mrs. Dimitra Goru. They come from company ASML. For those not aware of the company, it's the company that is actually behind the microelectronics era that we live in at the moment. It's the company that does about, I think, 80% of the equipment used in modern chip manufacturing. So, and the presentation is about the application of AI and the challenges it faces in semiconductor manufacturing analysis. So it's going to be online, and we already have them. So hello, can you hear us?
Hi.
Okay, so please, the floor is yours.
So, good afternoon to everybody involved. We are Alexander and Dimitra from ASML, and we speak to you from Veldhoven in the Netherlands. And we'll discuss a few things on AI challenges and opportunities in semiconductor manufacturing with you. And as mentioned, we are a part of ASML Development and Engineering in the Netherlands. Yes, so a little bit about ourselves. I have a background in machine learning already a couple of years ago. My thesis was on the use of machine learning methods for the monitoring of rotating machinery for predictive maintenance. And after several research positions, I moved to ASML. I've worked as a data scientist, as an architect, and since 5 years, I'm the group leader of a group now that focuses on predictive maintenance and diagnostics.
And I'm Dimitra. I will continue in English because my colleague Alexander doesn't speak any Greek.
Sorry.
So I finished my diploma in the University of Paris on Computer Engineering and Informatics departments. And after that, I came in the Netherlands in Delft University of Technology, where I did my PhD studies in graph methods. After that, I had data science positions in a company, Exomnia, in a consultancy company in Amsterdam, and I joined shortly after that in ASML, where I continued as a data science and machine learning architect, and currently I'm also a data and analytics manager. And we are going to give a presentation about our work here. Amazing.
Let us show you this animation of how chips inside your mobile phone are actually built up. And this may not be obvious to everybody, but we're looking at nanoscale structures. And we'll explain a few things on the process to make it and the role of our machines there. So basically what you're seeing is we zoomed in into the smallest structures of a nanochip, and there you see very small structures that are stacked on top of each other, having regular structures like, for example, line spaces, and then connected via interconnects, contact holes, and what have you. Of course, the whole process to print these miniature structures is something that we do with lithography. We have a global presence, so our headquarters is based in Veldhoven, the Netherlands, several offices in Europe. We have manufacturing facilities in the US, on the East Coast, in Wilton, near New York, but also in Silicon Valley and in San Diego. And we have many local offices near our customers in the East, and that totals over 42,000 employees year-end last year. Lithography is, of course, about writing in stone, literally speaking, but we use light for doing that. And you can make a bit of a parallel on the old photo enlargers from the past. They may be even unfamiliar to some of you these days, but there the idea is to enlarge a pattern on the sample in the top. But what we do is the other way around. Based on the pattern on a glass plate called a reticle, we are miniaturizing that on a silicon disk, which is called a wafer. To have an idea on the scale of that, so we try to make a parallel there. So wafers, those are the silicon disks that are used as the baseline. They have typically a diameter of 300 millimeters. And a few years ago, the typical feature size that could be printed was about 38 nanometers with an accuracy of about 2 nanometers. And all of that happened at quite a high speed, 250 wafers per hour. These days, the numbers are slightly higher, I have to say. And that basically can be translated in the following way, just to have an idea on the scale. Look at the Netherlands. We are a relatively small country, but our diameter is about 300 kilometers. And that corresponds actually to 3.8, let me check that, because there's a window, centimeters with a positional accuracy of 2 millimeters. And we can do that, so we can print all the features of the Netherlands at that scale in 50 seconds, 15 seconds. That is quite amazing if you think about it. Now, here is how that system looks like. This is a fairly large and quite complex system. We feel it's one of the most complex systems in the world, actually. The scale of this is the scale of a small bus, you could say. And there you see in the heart the reflective optics, where we are actually focusing a beam of extreme ultraviolet light onto the wafer, and the wafer you see on the bottom there. You see actually on the bottom of this animation, on the left side, the next wafer is being measured, and based on the position deviations that are measured there, we can have dedicated corrections already applied during the exposure side when the wafer is put to the exposure side of the machine, and there actually the pattern is being transferred. All of this is automated. You see on the top also the reticle handler. Everything in that sense is automatically transferred into the machine and out of the machine at quite high speeds. The extreme ultraviolet light that has been designed to be made in a quite intricate way. So there we are generating plasma by firing 50,000 times per second on molten tin droplets. We create a plasma, and by that extreme ultraviolet light of 30 nanometers is being emitted. And by this very small wavelength, we're able to print very small structures on the wafer. This is exactly what you see here. This is, of course, a schematic where the plasma is being made, and then the extreme ultraviolet light is being emitted here. And this is state of the art in the world at the moment. With that lithography step, basically we are supporting our customers to make chips. What our customers are doing is building, stacking layers on top of each other where the patterns are being carved out, so to speak, by light. And so here you see the silicon wafer, the substrate. There's material deposited on top of that. And then there's a layer of photoresist is being put on the wafer. And then the glass plate with the patterns that need to be transferred is then put light on. That's what you see here. And in this case, where the light is hitting the photoresist, it's being developed. And after develop, then you see that the pattern actually is carved out here. And after that, it's still only in the resist, but then we need to do the etching, at least that's what the customers do. And then the pattern is etched into the material. And then based on that, do some post-processing, and the next layer can be stacked on top of it. Now, this is a process that repeats itself hundreds of times these days. And after each step, there is all kinds of chemical thermal treatments to the wafer. And in the end, you will see stacked functional elements, like the one that we already saw in the animation. And this, in the end, leads to a functional chip that is being chopped off and being packaged in, for example, your mobile phone. Now, there's a lot of variations that happen inside this process, and controlling these variations is key. That's also where we use different machinery for. So we have dedicated metrology tools that we also design and ship to customers. And based on the on-product measurements on the wafers, our customers can use that to set up a control loop to the scanner to control for variation that is present due to the process. Well, here are some examples of variation that we may see. So what you see here is a wafer that has been separated in many, many fields. And you can sometimes see physical effects that extend themselves across the wafer. And those can be seen to lead to, for example, positional errors that are landing on side of the wafer. And these patterns are not always random. What you see here is clear structure due to, for example, annealing in the top left, or due to mechanical polishing, and there's many known effects that find their way into positional deviations on the wafer. So by recognizing these effects, we can also start to correct for them, and that's where you see the link to data science happening. So data science, and in more general sense, AI can be used in many ways. So once again, for process control and variation reduction, we use it to help our customers go to a yielding process as soon as possible. But it's also to monitor our own equipment. Like if there is something going wrong, that we can diagnose as fast as possible what the actual root cause was. And by doing that, reduce the downtime. And of course, we'd rather prevent downtime by having proactive means to monitor the parts in the scanner. And next to that, there's also new opportunities like optimizing across our supply chain, and of course, use AI for the greater good, also to minimize the energy efficiency or optimize the energy efficiency of our tool.
And continuing to this, actually a typical fab produces terabyte of data every day. So here in this picture, you see a schematic of a fab where it has the ASML lithography machines together with polish etching tools. All of them, they have to work very well integrated together for the perfect exposures. The fab is very tightly controlled and monitored. And each step of this, they have sensors, dedicated sensors that may measure that step, producing actually abundance of measurement. So that's how we end up 2 terabytes of data. And an ASML has around 6,000 machines in its installed base. So it looks like it's the ideal place for machine learning. However, if we look closer, what we can see is that we typically end up with small data sets in our setting. So in this fab picture, we have unrestricted access to the data produced by our machines, ASML scanners, while a big part of the performance of those exposures belong to our customers. It's considered customer data because it's the data that are produced by their production process. And that has some data quality and availability challenges for us. Let alone what is the most valuable type of information for us. It's our labels in machine learning. It's metrology measurements, it's performance measurements that they are a bottleneck in production. It's done by tools that they don't do productions, but they measure how well the production is. So it's always lowest priority. Also, the second challenge that we have in order to apply machine learning and AI in our ecosystem, it's that an ASML machine, it's very complex. It consists of hundreds of mechanical components, which they can age differently, and let alone the other tools in the fab, and that results in complex dynamics that we need to take into account. And of course, as it was mentioned by Alexander in the introduction, we expose wafers with around 20 seconds per wafer. So that puts a lot of speed extra constraints in our AI machinery.
Mrs. Goro?
Yeah?
Sorry, can you hear me?
Yeah?
Is it possible to speak a little bit louder? We can hear you, but not very, very clearly. Thank you.
Okay. So, we also have, because of this segregated data landscape, we have diverse environments that we need to consider. So, also our scanners, they produce a lot of data that we cannot transfer back to train our models. So we need, there are also challenges that edge computing could be relevant. In order to deal with these challenges for applying machine learning, what we have learned in our journey here is that we need to combine machine learning and AI together with domain knowledge that can have different forms. It can be models of physics, or it can be knowledge on the mechanics of the machine, so that we can get the best of both worlds. AI and knowledge-based systems, physics-based systems. So on one hand, we can have the accuracy that AI and computational efficiency that AI give us, the ability to integrate heterogeneous data and have uncertainty quantifications of our estimations. And on the other hand, having the generalization capabilities of knowledge, having interpretability in our models, awareness about causality and context, something that machine learning and AI cannot do alone without support from knowledge system. And of course, for our limited data set, integrating knowledge help us to not have data hungry algorithms, but work with efficient data schemes. We have different strategies for doing that. So we can operate with domain knowledge on the data by doing data transformations or feature selection and engineering. We can augment our data, or we can integrate that knowledge in the models, like constraints in our cost functions or prior knowledge. We can make informative model assumptions, or we can even encode this knowledge in the architecture of our machine learning models. And when that knowledge is not structured, we have iterative interactions between machine learning algorithms and domain experts, active learning or expert in the loop, or domain experts interpreting. So in the rest of the presentation, we will give you an example of each of these big three categories.
Let me start with the first example, which is on getting domain knowledge present in the problem formulation itself, also in the design and also in the feature engineering, obviously. The example comes from predictive maintenance of our scanner. Here you see an example of the TwinScan, which is our deep UV scanner system. These systems are quite abundant in the field already for very long times. And after many, many years, you might see some of the parts sometimes start to wear out. And of course, if that would happen in a late state, that at some point in time, our customers might get impacted, and we want to avoid that as much as possible. And so the aim of this type of work is to come up with predictive model alerts that are alerting us in time of any degradation, so we can in time have the service in place before there's impact to our customers. Now, the challenge in this case is to come up with a setting where we use our own prior knowledge from ASML, our domain knowledge, but at the same time leverage the many, many data that we have around it, the measurements inside the scanner or around the scanner. And so there's a component degradation that might happen. And of course, we want to use that for scheduling proactively the service to the customer. And what you then see is next to, for example, the wafer fingerprints that you saw earlier, there can also be degradation fingerprints, slow trends or changes in the time behavior of the measurements that we see. And that typically leads to time series parameters that we're measuring on the scanner, where we look at methods like sequence classification, also regression and forecasting methodologies. And those are used to come up for multiple parts, basically traffic lights. And is the part in good condition? Is you basically see, do you see the parts start to slowly degrade, or is it already in a far degraded state? And that also then leads to an action plan that can be adapted to the situation. We use that for providing predictive service to our customer. And we're using several mechanisms to keep the models up to date. Like we're using principles from machine learning operations, the software methodology around industrializing and updating the machine learning models, and also active learning as a mechanism to integrate domain knowledge while the model is being deployed in the field. Now, how does that work in more detail? So here you will see a schematic of how our setup is currently. When we start with the use case, there's functional knowledge about the part. There's also lots of data and machine context around it. And we have a bunch of means and methods developed on data science and data engineering to support all of this. And we have a cloud-based environment where together with domain experts, we do the feature engineering, model development and validation, and this is being iterated until the moment that the model is of sufficient quality so we can go to production. And we have a more automated CI/CD setup there, where eventually in basically the fields, so to speak, we have an industrialization setup where the pipelines are running per failure mode. And the pipelines, they are providing the output, the key performance indicators for the health of the parts to our customers. And the customers are, for example, our own customer support organization who makes use of the KPIs, the data that we provide to them via the data mesh principle. Now, of course, we know that when models have a dependency on data, we need to basically monitor whether the model is still up to date. So there's a performance monitoring in place. But also can be needed to update the model by the automated training. It could also mean that there can be new insights along the way. So via active learning, we allow our domain experts also to give that new insights or new labels while the model is being deployed.
So the second example, it's an example from diagnostics where we encode the domain expertise in the architecture of the model. So just looking at the picture of an ASML machine, when an issue happens in that complex system, several other sensor measurements, and the sensor starts saying an alarm, several other sensors start indicating alarm, having actually many deviations in the machine, and identifying which of these hundreds of mechanical components has an issue, it's extremely challenging. So the machine has 10,000 of sensors that they will start showing issues. But on the other hand, sometimes also the sensors can be wrong, they can be not accurate. And this is why we are using domain expertise to complement our data there. So when causality is not always easily deducible from data, we complement data with domain expertise. And to which level we have this domain expertise integrated in our models, what is the right abstraction level, it was quite challenging for us. So the solution that we have, it's we built a causal graph based on domain expertise, and on top of it we have mechanism in machine learning called Bayesian networks that allows us for probabilistic reasoning on top of this causal graph. Just to show you a schematic of how this works. So we have on the lower level of this system the health measurement, the health indications from the sensor measurements, that they can be active in multiple places, indicating potential issues in multiple places. On a layer on top of that, we have our causal graph, which actually captures the interactions between different modules. So what you see in that schematic of a graph in this picture, its a node represents a module in the machine, and the edges their interactions. So it's the causal graph that allows us to do the reasoning. And on the top layer of our system, we can reason which module is broken with the highest probability, and disentangle actually those effects that we see there. And the second example, in the third example, sorry, that we present you, it's a bit of when we have the human in the loop. So a human in the loop also, that as we said, it can go to different stages of the machine learning procedure, from pre-processing, training the models when a domain expert can interpret the results, or even during deployment, a domain expert can monitor and interpret different decisions of the domain of the machine learning model. I will show you for the pre-processing part what we do, very high level, how we use human in the loop in order to do feature engineering, for example, something that is important for us for training our models. So we develop applications which load raw data, and these applications, they give informative visualization to our domain experts. Domain experts, they can query parts of the data that they would like to investigate. And then high dimensionality, the high dimensionality of the data can hinder identifying the proper patterns that we want. So the dimensionality reduction techniques together with visualization help domain experts to make sense of those data and give feedback to the application with their domain knowledge, and do this iteratively. For example, if we have data that they present some clustering structure according to some dimensionality reduction techniques. Domain expert can make sense of that clustering structure and see if it's common process parameters or something else. Give that information to the tool by really drawing the proper clustering, for example, of the data. And this operation will have a normalizing effect in our data. We encode this knowledge by normalizing according to the clusters. And to do this iteratively, then domain experts had to characterize all the structure that exists in the data. And that's enough for us to train our machine learning models and have the benefits for that. So that results in better interpretability and control. Nevertheless, we should think that this combination of knowledge and machine learning, it's not trivial, because how domain expertise might be biased, inconsistent, might come from different sources, and it can be difficult to integrate. And also in terms of the system requirements, it's difficult how we maintain it and we update it, or how we preserve our IP while this type of systems run in customers, how we build trust for humans in the loop. All these are difficult challenges.
Yeah, so with that wrapping up, we have some main take-home messages. So data is very important. We can use it to complement the detailed technical functional knowledge that we have to see what happens actually in the field and to optimize it towards that. Of course, we need to have proper quality data available then. It should be reliable, it should be trustworthy, and that is of course a necessity. Here is also, for example, an area where edge computing could play an important role going forward. Knowledge and AI together unlock the potential of AI. It's not just learning from data. We also feel that purely knowledge-driven might not reflect always everything that happens at our customers in the field. So the combination of the two and getting the right methodology to combine them, that is key to make this successful in our reality. So we presented several efficient strategies from our own experience to integrate knowledge and human inputs there. And also we mentioned some of the challenges that embedding this knowledge in AI is not a trivial thing. We want to make it not too specific on the individual human biases. The knowledge elicitation procedure should be scalable. Also, the interface towards the experts in the loop should be optimized. And also there is notions of efficiency, and also that humans in the end need to use this information. For example, our customer support engineers to do effective troubleshooting and follow-up. And with that, we'd like to thank you for the attendance that you have. And yeah, maybe we should open the floor to questions.
Thank you very much for this very enlightening presentation. It's really it's very interesting to see the level of complexity you people tackle in ASML. One machine, 10,000 sensors, more, let's say, of the industries at the moment. So are there any questions on this presentation? I have one, so I'm really not an expert in this domain, but you mentioned at the beginning the problem of data availability and data quality. And for me, it's a little bit puzzling because as ASML, you probably control most of the sources of the data, but the equipment is your customer's equipment, so the data are probably also your customer's data. So in practice, how difficult is this problem?
That is indeed a very good observation. Data is not always available as such because it's customer proprietary data, but it can be in the interest of the customer, and we do that in good collaboration to have still some data exposed to us to be able to provide the proper service level. And that is a collaboration that we do together with our customers to optimize it, but it will be done on a case-by-case basis.
Exactly. Just to keep in mind that our customers, they are direct competitors in a very competitive landscape. So that's restricts them from giving us direct access to their data.
Okay, and there is another question from the audience, from Mr. Diamandopoulos from IBM. Maybe you can state the question and here's the microphone.
Hi, I'm Dionysios Diamandopoulos from IBM. Thanks for the enlightening presentation. It is really great to see how you are using AI on those systems, right? The top lithography systems in the world. My question is, I have seen that you are using a lot of label data, and especially when I have seen these slides with label data from the clients, which I suppose it's a very tedious process to, label them, maybe. And I'm wondering if you are exploring any kind of unsupervised learning techniques. I have seen that you are using clustering, probably K-means or something like that, which is going along these ways. But if you are considering, or you have considered any kind of unsupervised learning techniques and moving further on, the new AI kind of models, like foundational models that they can somehow learn automatically some of your patterns and try to, keep the labor manual work of labeling, which I speculate that you also saw that in the challenges, right? Is it can be based on human bias, so it can be very tough. Yeah, this is my question. Thank you.
Yeah. So the variations that we see, it's a process that it's very tightly monitored. So the variations that we see, it's very small. It can be typically up to 5%, I would say. And also the reason that we have a domain, so it's very difficult to learn them from data what exactly they mean. And the most interesting part from us to learn is why we see those variations. So this where the labeling and the domain experts come. So we need to act upon what our machine learning models give. Of course, we investigate unsupervised methods as well, and we see them more on the exploratory phases of the problem or for interaction with domain experts. Typically, I would say most of our cases are supervised machine learning. Would you like
No, I think the active learning already points a bit into the line of thinking. Some things you can already distill purely from looking at the data itself, and then we get targeted ways to get domain expert input to further enrich the modeling. I think that's typically what's needed, because we need to be very sparse on how we can engage those experts, because they will be needed for many, many things. Yeah. Yeah.
But we are looking to be also for very rare variations.
This is the last question.
Yeah, hello. Thank you for your great presentation. I am Anastas Xinos from NTUA, PhD student there, and mainly working with FPGA. So my question is, seeing the trend towards very, very small processing nodes, and now the demand for many new facilities in the United States, and the competition between the companies, has your research, based on the previous problems, I remember Intel's then 10 nanometer node had many, many issues, and they couldn't achieve large production numbers. Has your research allowed you to provide your customers, Intel, TSMC, and others, with technologies and good practices during the actual building of their facilities to, let's say, guarantee less problems and less time to market?
So thank you for the question. Yeah, I can only give a general answer. So there's many efforts in ASML to support the customers as good as possible. So what we are highlighting is some of the more data science-driven elements, where we start to use AI for some of the elements, for specific problem statements. But in general, there's quite a large service organization that is on a daily basis supporting our customers in node transitions and supporting them to ramp up. So that happens on a daily basis. In that big endeavor, we see now that we also start to make use of AI and data science as one element in the toolbox to support the customers. Rita?
So thank you very much.
Thank you.
For your presentation. We're really very pleased to have you in our conference, and we look forward to see you also in person, if you'd like, to our next conference next year. It's in Crete, so nice destination. So thank you very much.